Today, I'll be demonstrating 4 of our applications, predominantly the Stockpile, Flotation, Grinding, and Thickener app, all of which are available to you today. I'm going to present them in the context of net metal production and how they can all assist in balancing your throughput and recovery to enable a higher net metal production whilst sustaining your sustainability goals. We start with the slightly less glamorous part of AI, which is data and getting it, which is when we walk into many companies and their digital journey is the first hurdle. Simple questions like, I don't have enough data, my data is not good enough, etc. To do this, we've never had this challenge. We've never faltered at this challenge. Everybody has enough data and it's good enough. As you can see here, for a single asset, I'm now inside Brains app, all the data coming through for this particular common configurable asset of a SAG mill. You can see it coming through and all the quality features that we're pointing out here automatically. But naturally, this is not the amount of data points that a standard SAG mill gathers through instrumentation. This has been put through all of our virtual sensors, which transform this data into additional insights and additional metrics. Those additional metrics are generated in real time, and all of this is generated in real time from multiple data sources. We can integrate with over 20 plus mining systems, whether that be spatial data, laboratory data, time series data. Just to highlight a few of the types of virtual sensors we can do, which are broad. You can see some financial metrics, which we can calculate in real time. You can see, for example, residence times of SAG mills and different areas around the circuit. In terms of kilograms per ton inside, in terms of ball consumption, all of this can be automatically generated through our virtual sensors, and down to important metrics that we need to start generating and looking at in real time, such as the specific CO2 emissions of the SAG mill in real time. Now that we have all this data ready to go, let's look at net metal production. First thing we need to do is monitor net metal production before we can actually talk about it. And so net metal production is a combination of 3 things: the feed grade, the throughput, and the recovery. What I'm showing you here is 2 different aspects of looking at net metal production. If you look at the aspect from geology and mining, you almost predict the net metal production based upon the geology and the mining plan, which is represented in red here. So you can see the slightly bumpy way in which we get to a new block, we get to a new area, and we can see, and for those downstream, we expect the same feed grade, we expect constants here, versus the reality, which is the variability of the feed grade is actually quite high at a lower level. Most mines, as you can see, I'm looking at this at a daily resolution. Most mines can achieve this. Understand a mine plan based upon geology, what will my net metal production be? However, if you want, which is the hardest challenge in mining, 2 disciplines to talk to each other, mining and the plant, we need to get down to a lower resolution. And to do that, often what happens is our stockpiling, which is the interface between mining and processing, is often where data is lost, as we only look at volume and mass. However, let's fix this feed grade to ensure it's consistent and that it's predictable at a lower resolution. To do that, we'll introduce our Stockpile application. The Stockpile application gives you a high resolution 3D model of your stockpile, generated as real-time data comes in. You can see here the formation of stockpiles, obviously sped up in real time, but gives you an idea of the dynamic nature in which we're building these. You can also see that we can track brand new metrics that one would never think of using this methodology. For example, the age of each block here being tracked dynamically over time, blue being new, and then as you can see, taking that new material away, you could imagine splitting this in half and understanding older material and how it relates to oxidation. This is generated in real time and can be seen in Brain's app as generated. So now we have our feed grade, but however, we can zoom in now and look at this world at a higher resolution, an hourly resolution. So we understand this feed grade, it becomes predictable, and we can align better the mine and the plant. Understanding now getting the most out of what we put in is the next stage. And to go to that, we need to go down even a lower resolution into minutely resolution and the flotation circuit. In the flotation circuit, one of the hardest parts of flotation is not necessarily the lack of data, but the lack of instrumentation in the right areas to get you the right information. For example, recovery. Recovery is often measured through laboratory, and so is reported about 4 hours after the fact. And so decisions are made not proactively, and so therefore our recovery as a result suffers. However, using, again, our virtual sensors to get real-time recovery, real-time concentrate grade, tailings grade, and mass pull, we can monitor in real time and proactively make changes to ensure we maintain our targets. We can set up alerts to ensure that we make the correct evasive action well in time. But flotation is also at the lowest level important. It's all well and good looking at high level, but we still need to drill down constantly. And so you can see here the alerts that we can generate going down through luffers to cleaners to scavengers, and even down to the cell level, understanding where we are at each cell and what the optimum material characteristics are, for example, the P80, P95 and densities inside, and the recommended froth depths we can play with here to ensure that our recovery is maintained. So if we have a constant predictable feed grade, we have a high level of recovery, the next thing we've got to do is put more material through our circuit. To do that, we need to grind it efficiently at efficient energy levels. To do that, for example, offline, we could look at our grinding circuit simulation. As Karen alluded to, we developed digital twins. And so this is our grinding digital twin, fully configurable to your site. You can see here all the different variables that we can configure it to, whether it be the type of moisture of the feed, the actual microns of the feed, but also the effective setup of our piece of equipment itself in terms of height, diameter, etc. You can see here a similar representation of it. So if I simulate what's going to happen next offline using this material characteristics, I can see a full circuit mass balance in terms of all the particle size distributions, but predominantly I can understand the optimum throughput, 1,100 tons per hour, that I can feed through this SAG mill. If I reset that and I use the information from my digital stockpile, and I know that the material is going to be slightly smaller, I could simulate again and understand that I could get 100 tons more through my SAG mill at a slightly lower kilowatt hour per ton, lower energy consumption per ton. So what I've described here is a way in which we can consistently have a feed at the best recovery, knowing the best material character at the highest mass flow. Next, what we've got to do is, and I've showed you that in an offline setting and in a virtual sensor setting, real time. However, we need to optimize these things proactively, looking into the future. To do that, we're going to look at some of our sustainability metrics. So we're going to look at water. Water recovery predominantly takes place in most mines at a thickening circuit, where the water is separated from the solids, and often problems occur here with pushing these pieces of equipment to the maximum, and the torque off of the rake often fails. Or in Karen's case, we use too much flocculant consumption in these areas. What I'm showing you here, and I think point out about the user experience, this is exactly what an operator on a mine sees. They see a different set of variables over time. But what they don't see is this 1 hour timestamp into the future and the predicted variables of the future based upon all the different material characteristics, based upon the state of all the assets before this, and the current running of that piece of equipment, including the uncertainty bands, which is about our transparent AI that we push at all times. From this, we can predict and optimize the future, right? Choosing a future we want based upon a set of value drivers. So you can see the change in the green control variables to achieve the optimum future in this case. Again, we have full transparency, and we can test out this digital twin and simulate whatever variable we'd like at extremely high speeds with incredible accuracy. But when I press that optimize button, right, what happens? Where are we optimizing from? How do we define the best? To do so, we have a configurable value driver for all of our applications. This is, knowing this, working on a mine site, aligning everybody to a common goal is one of the hardest things we can do almost in any business. However, we configure this, and this is some examples we've done with people on different mine sites about what they'd like to get out of each piece of equipment or each process. For example, maximizing sustainability, recovery, or throughput. If we look at an example of this, setting different variables up different ways will have a different outcome. Weighing flocculant consumption over recovery will reduce costs, or understanding how much water we get out versus the throughput will help our sustainability goals. The power of AI allows those decisions to be made and that balancing to happen for us. Once those decisions have been made, probably one of the hardest parts of any AI transformation is getting people to follow and trust and use AI. And so with that, we have developed a simple to use screen where we can deliver the recommendations to our final user, our operator in this case, as to what the recommendations are and how to follow them. But transparency is everything here. And for example, I've got 2 thickeners. You can see one is in full operation and the second one is not giving me recommendations. I'm not forcing the recommendations because I've poor data quality in this case. Nobody wants to hear a recommendation with this kind of data coming through. However, the transparency is always there. And if required, this, with training, one can understand how to read what is going on inside the optimizer's brain. And so that's presented at all times to our final users. So this together will have a high benefit on our process, but we obviously want to track those benefits and present them back, how AI has affected our process. And so today's theme was about net metal production and the balance between recovery, throughput, and how our set of applications can help on the bigger scale. To do that, again, we need to track everything if you want to report on everything. And so, for example, net metal production can be reported almost at a minutely scale based upon your production, but also different sustainability variables such as the kilograms of CO2 per net metal production can be reported almost on a minutely scale. And so decisions on a mine amazingly can be made based upon what is happening right now to our environment. If I summarize, and this is a culmination of all the data that we've seen today, before IntelliSense, with IntelliSense, and some of the benefits, the feed grade in this case, using our Stockpile app, will remain the same. However, the predicted downstream variability will improve. There's a very small variability here, but we do have a higher variability of predicted downstream. So we understand our feed grade better. Using that, we can increase our throughput. In this case, the optimizer or the value driver for this site has identified that recovery may go down in the higher case of the throughput. But it's about balancing in this case to ensure that, for example, our net metal production goes up. So by 10%. In terms of the thickener, we can make a giant improvement in the underflow percent solids with this throughput and recovery, and an understanding that we need less fresh water being pumped to our mine. As a result, we probably use the same amount of energy in this case. However, because we've produced more metal, we're producing less energy per net metal produced. As a result, if we look at how that converts into our sustainability metrics, our CO2 per kilogram of net metal produced is reduced by about 10%. The recycling rate of our water goes up, and our fresh water per kilogram of net metal production also goes down by 11%. Overall, being able to use our applications to balance everything within your circuit, from the material coming in and making that predictable and understanding the best way to process it, will help our planet and the sustainability goals of any mine. So I'd like to invite you to come and talk to IntelliSense about how we can configure this solution to your mine.